Motors are a very important piece of electrical utilization equipment. They are used to turn equipment such as pumps, fans, and moving systems like conveyors. Motors are also used in factories to crush, form, drill, and stretch materials in production. Motors are turned on and run for short periods of time or very long periods of time. Being able to control motor speed makes the motor more useful, and many times it makes the process more efficient and even safer. The electrical apparatus that helps control motor speed is called a variable speed drive, a variable frequency drive, or adjustable speed drive. For purposes of this course, we're going to refer to it as a variable frequency drive. So you see, there are a few ways to control the speed of a motor. It can be controlled mechanically with pulleys or by changing the voltage and current going into it. But one of the most efficient ways of doing it is by using a variable frequency drive. You see, a variable frequency drive controls the speed of an AC motor. It converts an alternating current signal, or the sine wave, into an adjustable frequency and voltage source. Then, this AC source is used to power the motor. The VFD allows the speed of the motor to be changed by manipulating the frequency. Here's some of the types of motors that can be controlled by a VFD. A hot water circulating pump, used to circulate hot water to heat around a building. A conveyor belt motor, or some other material moving equipment motor in a factory. A motor that drives a fan or blows other air for an HVAC application. You see, all of these motors have a set speed, also known as synchronous speed. That's the speed at which the motor is designed to run when the full normal voltage is present. But sometimes, the speed of the motor does not match the exact application or work that we want to accomplish. We need to find a way to slow the motor down, and in most cases, control the speed so that we can get the work done efficiently and sometimes in step with other processes. There are three major components that all variable frequency drives have. They are a rectifier section, which is a group of electronic components that convert the incoming AC current into DC current, usually using diodes. A DC bus section. This is where the converted DC current lives and is manipulated, typically to reduce the DC strength that will be converted back to AC power with a different frequency. And an inverter section. Here, the manipulated DC current is converted back to useful AC current for the motor. When a variable frequency drive is in use, the voltage arrives on the left-hand side here, or the incoming section, where it goes into the rectifier. The rectifier then converts this AC signal into DC, and it leaves the rectifier and goes into the DC bus. Within this DC bus, the current is then switched on and off, repeatedly and quickly. This helps the drive create this artificial type of AC current. Then the power is handed off to the inverter, where the DC is converted back into an actual AC signal at a particular frequency. This is a frequency that is known to drive the motor at a desired speed. In addition to these components, most variable frequency drives have some sort of operator control that allows the operator or user to command the motor to function as desired manually or through the use of motor control inputs and outputs. 2. A housing, some sort of housing that's suitable for the environment. VFDs may also have a fuse section designed to protect the motor and the sensitive electronics on the drive from dangerous currents and spikes. A line reactor. This reduces the harmonics or electrical noise associated with VFDs. Input line reactors are common on most applications. Communications electronics interface, or communications device. This allows the VFD to be commanded by an external program, an external user interface, or by signals produced by remote sensors. Dynamic braking. Dynamic braking allows a VFD to electrically assist in stopping a motor. This may include resistors to help absorb some of the voltage that would normally go to the motor. You see, there's a lot of other options that a VFD may have to help control or monitor a motor. These are just some of the most common ones. Now that we've talked a little bit about what a VFD does and what's inside of them, let's discuss installing variable frequency drives. You should always make sure the variable frequency drive is sized appropriately for the motor and the load that we are trying to control. Most VFDs need to be mounted or installed as close as possible to the motor that is being controlled. Excessive cable lengths may alter the performance of the VFD. Many VFDs require the use of special shielded cables, also known as VFD cables, from the output side to the motor. Check with the VFD manufacturer for specific requirements of that VFD. VFDs have sensitive electronics in them. They should be installed away from other magnetic sources and in an area that is safe for solid-state equipment. Moisture and high temperatures should be avoided. Some VFDs require a separate external power source to power the controller and accessories on the VFD itself. Once again, check with the VFD manufacturer's recommended installation practices. One of the key benefits of using a VFD is creating a process that is efficient, safe, and in step with other processes. Having the ability to not only control the speed of a motor, but having the speed adjust to meet the demands of the user make a VFD an extremely useful component in an electrical system. In order to achieve this specific amount of control, programmers and input sensors are used to let the variable frequency drive know what's going on around it and what is expected of it. Computer applications such as temperature control or building management system, also known as BMS, Ethernet or TCP/IP, BACnet, and many other protocols are used to control a VFD. Here we see a user interface for a variable frequency drive that can be programmed manually by pressing the keypad buttons and entering the parameters desired. In addition to this, many variable frequency drives are capable of interfacing with a standalone computer so that a one-time program can be uploaded into the VFD microprocessor, or continuous commands from the BMS system or temperature control computer can be sent to the VFD to match up with other parts of the building. As an example, if a hot water circulating pump was heating part of a building, and that part of the building got too hot, the temperature sensors located throughout the building would tell the computer that it was too hot, and the computer would then in turn send a signal back to the VFD to slow down the hot water circulating pump, therefore reducing the temperature in that part of the building. Another example of this would be a conveyor belt system. Let's say part of a manufacturing process was producing 100 cans of mojito drinks a minute, but then there was changes in the process and it needed to slow down. The sensors in the production equipment would tell the VFD that was running the motors that moved the conveyor belt to slow down so the other processes in the factory stayed in step or proper time with the production machine. Sensors such as temperature sensors, proximity sensors, limit switches, pressure sensors, timing switches are some examples of sensors used to help control a variable frequency drive.